Hello, class. Let's have a go at Bernoulli's equation. Right, we're in the fluid dynamics chapter, and we're to Bernoulli's equation, which is kind of a Swiss Army knife of equations. You can use it in so many different circumstances. It often simplifies down to really tractable subparts, and so it's super useful for a lot of situations. Assumptions we got going are incompressibility for your fluids. So your fluids, think water here. Gas is really not a good example of an incompressible fluid. So water, transmission fluid, things like that are incompressible. Frictionless fluids don't exist in nature, but we're going to pretend they're frictionless anyway. And a lot of times we use this equation for air, even though gas is clearly compressible, meaning that if you took some and then you put it in a box and squeezed it, it would squeeze down. I mean, it's not going to resist like water would. But we're going to pretend sometimes air is incompressible as well. Basically, the symbols. P is for pressure, so that's your capital P for pressure. And pressure has units of energy per unit volume. If you take a glance at the units, so the amount of energy divided by volume, you get the same as pressure, which is force per unit area. So force divided by area, that's pressure, but you could recast it. You could think of it as energy per unit volume, and that's Bernoulli's genius there. So he was thinking of it that way. And then, and this is clearly a kinetic energy term, again, per unit volume. So that's your kinetic term, and we know that because it's got a velocity in it. So that little v there is for velocity, and rho is density. So 1/2 rho v squared sounds a lot like 1/2 mv squared, but mass per unit volume is density. So that's what that equation, that term is. And then this one, you see the rho gh, well, that's almost like mgh, and that's gravitational potential energy. So this is the gravity term here. All right, so one thing to note about it. Let's do an example where we simplify it. So this is this equation. These three terms are equal to a constant. So basically, you're thinking of some transformation taking place: water in a dam, water in a fire hose, air over the wing of an airplane. There's some kind of transformation going on, and you want to characterize that. So you use Bernoulli's equation. Let's use it right now to recover our formula, pardon me, our formula for our statics formula for the increase of pressure with depth. Of pressure with depth. And to do that, we think of maybe a parcel of fluid at the surface of a container and then one deeper down. And things are not moving. So this is a statics problem. But let's just write Bernoulli's equation, and let's write it as if it's a constant, but so that means we're transforming it. We're looking at the surface and then at depth. And so surface will be 1, and at depth would be 2. So we'll put some subscripts on things. For example, the velocity term, which we're about to set to 0, and then rho g h1, and that is unchanged with depth. So at depth we got another pressure and another 1/2 rho v2 squared and a rho g h 2. All right, that looks good. But we are static. So we can say velocities are 0. So those terms go away. And then if you were tempted to put subscripts on the densities, good job. But we're assuming this fluid is incompressible. So those densities stay the same. So they don't need a subscript because you never change the density because you can't compress it. All right, so what's left? Not a lot. This term, that term, that term. So I've got 4 terms left, and a lot of them are equal. Let's subtract P1. So we got P2 minus P1. Then let's subtract this term over here. So we get a rho G, and then H1 minus H2. Kind of like that. So that's simplified quite nicely. And we can say that, okay, pressure change, what's that? Well, that's a delta P. And so that's equal to rho G, rho G, he says, delta H, or H for short. So I've got my symbols in the wrong order. Wahaha. Well, that's cool. Actually, let's back up and box that up. Except for the wrong order. This is, okay, it should have been delta P. It's rho G H. I don't know why it has to be in that order. Anyway, this is just the change of pressure with depth formula from last chapter. So Bernoulli's equation has it in there. So anytime you need that, there it is in Bernoulli's equation. All right, let's look at some second consideration. I'm just going to run through some examples, and let's look at wings and sails. So these are practical things. If you're gonna put a wing in, like an airplane wing, it's tilted downward a little bit, and also the shape is such that a parcel of air coming in the bottom can travel kind of under the wing, but then if you're a little bit over that, the air has to take a kind of a circuitous path on its way around the wing. So this is supposed to be the cross section of an airplane wing. They kind of got a flat bottom, and then they're tilted a little bit, and then the top is bowed out like this. Well, path-wise, you can see that's a longer path on top, so the velocity is going to be greater. And that turns out, so let's call that number 1. You got a pressure and velocity up there, and then down here you've got a different pressure and velocity. So the velocity ought to be higher at the top of the wing because the air has to move faster to get around the curve. And in this particular one, the change of height is basically 0. So it's there's no significant change of height in this problem, so we can probably ignore that. In that case, we can drop that rho GH term, and Bernoulli's equation is like this. So pressure, and then 1/2 rho V squared with ones, and that should be equal to the other situation. So P2 plus 1/2 rho V2 squared. So if we look at the pressure difference again, so let's subtract P1 from both sides, and then we'll subtract that thing from both sides. So we got 1/2 rho V1 squared minus V2 squared. Like that. So we were saying that at the top of the wing there, that's got to be a faster velocity. So this V1 is bigger by a little bit, usually just a little bit. So this is going to be positive, and so we're going to have a positive delta P, where P2 has to be bigger than P1. So we have a positive pressure there. So P2 is bigger than P1, and what this what this leads to, of course, is lift. So as your airplane goes along, and this is equivalent whether that's air moving over the wing or if the wing's moving through the air. The other way, it's the equivalent situation. Anyway, you get lift, so you get some aerodynamic buoyancy there. And let's keep going. So let's do a couple more examples of Bernoulli's equation and how it boils down to useful things. Let's do a dam. And the idea here is we got some, I'll do my picture over in this corner. So we got some water level, and then we got a device to contain it. So we have some dam, and then let's make a little tunnel through the dam at the bottom where that joins. So this is supposed to be water over here. And then that water might be forced through this tunnel, and it will come out this side with some velocity. So we'll call that one V2 there. And in this and so this is your dam. Oop, different hatching, please. Thank you very much. Different hatching, that's your dam. And then we've got a height difference. So we've got an H2 down here, H1 up there. What else? Up here, V1 is 0. Let's see what else we can figure out. Aha, P, pressure. Pressure 1 has got to be atmospheric pressure. What about P2? So P2 down here, turns out, well, that's out in the air too. So this is also atmospheric pressure. Ooh, I sense a 0 coming along. That'll be very handy. So the pressure from the surface of the lake down to the jet coming out here is the same. So the basic change here, you're going to expect some gravity. So you got some H happening here. And then we've got a big velocity increase here as well. So if we write the whole equation, so let's do it, P1 plus 1/2 rho V1 squared plus rho G H1, and that's equal to everything with the 2, P2 plus 1/2 rho V2 squared plus rho G H2. Doing okay so far? All right, some things go away. P1 equal P2. So those things just disappear. P1 equal P2 equal atmospheric pressure. So they subtract away. V1 is 0 also. That water there, not moving. Let's do it this way. Let's call H2 0. And so we can call H1 just equal to H. How about that? Okay, so you look at these things. V1 is 0, that disappeared. P1 disappeared. P2 disappeared. So we have rho G H1 equals H is equal to 1/2 rho V2 squared. And then this thing, H2, we thought that was going to be 0. We set that to 0 just for convenience, and that simplifies down very nicely. If you solve this for the velocity, well, let's do it. So the velocity, there's a couple of rows, they cancel. They just go away. So the velocity is just going to be the square root of a 2gh. Is that still showing up down there? Great. So that is our kinematic result as well. So we've simplified once again. For a frictionless fluid, you'd expect the jet down at the bottom there to be shooting out at exactly the same speed that a dropped object would be going. That is nutty, isn't it? Gotta love those things. one more thing, one more consideration, one or two. I'll keep going for a little while. Let's take a picture and look at this fire truck pump business. So you got a fire truck. It's got a pump at the bottom. It's got a hose, and then the water travels up there to what they call a nozzle. So the nozzle just means that the hose gets narrow and shoots that water out at the business end of the fire hose, so to speak. So there's some really primitive schematic that we should draw. So there's a hose, and then it rises in height, and then it narrows down. So there's some kind of nozzle at that top, and then it comes out. So there's a jet of water. So yeah, let's call that V2 right away. There's a height difference. So that'll be H2 at the high end and H1 at the low end. What else? There's some magic down here at the truck, and that magic is that you've got some pump which pushes that water, and that applies pressure to the water. See, a pusher pulls a force per unit area is pressure. So there's some P1 down here, and that is what we might think of as a pump pressure. And there's also flow through the tube. So now we have to take a step back one section. Remember our letter Q. Q is flow. And if we're talking about hoses and pipes and so forth, it's the cross-sectional area of that hose or pipe times the velocity that it's going. This is actually usually useful in these fire truck problems. That's nearly all I want to say there, but I forgot one thing up here, which is P2. P2 is out in the air. So this is going to be atmospheric pressure. Out there. And then you supply some pressure, that water is going to travel up the tube and come out the nozzle. And so to seal the deal here, at the bottom, A1V1 has to be A2V2 at the top. So the nozzle narrows. So that's going to be for your nozzle up there. V2 is that V2. So it's the velocity of the jet coming out of the nozzle. A1, that'll be your diameter of the hose down at the bottom at the fire truck end. So A1 V1 is going to be the velocity of the water coming up the hose. All right, so what am I trying to say? I'm trying to say we got everything here. So we've got, we're able to solve problems like this, but this is the strange situation. And the counterintuitive thing is this pressure at the top. Why should that be atmospheric pressure? Well, it's out in the atmosphere. And then the pressure at the bottom, for the case of a fire truck, that's artificially bumped up, so you got a nice big pressure down there. And that pressure energy has to climb the hill with rho GH and also accelerate the water out the jet. So there's a kinetic energy that has to be supplied as well. All right, so the final thing is talking about power. Power was energy per unit time. And power in fluids what you do is you take Bernoulli's equation, and you have to take a while to spell it. Bernoulli's equation. You take Bernoulli's equation and then you multiply by flow. How about that? So power becomes Bernoulli's equation multiplied by flow. So if I write all that, that is pressure plus 1/2 rho v squared plus rho gh. And then we just multiply by q. And then like before, this one has to do with energy. This is an energy conservation thing. So this is energy supplied by your pump, or possibly gravity, or possibly internal energy from the fluid. But mostly it's going to be something like pump power there. And this is going to be kinetic power as well. It's got a V in it. And then this term here is again gravity. So it's transforming to gravitational potential energy. How much, at what rate is that happening? Well, it's rho gh times q. So we use this once in a while to estimate things like, if you look at the fire truck problem, how much energy do you need to maintain the gravity climb and the kinetic power that you're producing at the nozzle? You can work that out using this equation. All right, so that is some interesting stuff regarding Bernoulli's equation.